Welcome back, everyone. Now it's time for our monthly event, Astronomy in the News. You may notice that some of our old hosts have departed, but we are back with a
They're
great show
still
for you
alive,
today.
but
they're not dead.
Yeah.
I am Jackie Whatamerger Jr., and I am happy to introduce our new news anchor, Andreia.
That's me. Woo! I'm Andreia, aka my real name is Andreia Carrillo. I'm Jackie's office mate and best friend. So.
Aww. Okay.
And I'm subbing for the news.
Vote now on your phones if Andreia should stay. Okay. So our first news story for the month is about a new exoplanet detection. So Beta Pictoris has been a prime site for research into young stars and planetary formation for several decades. It's located 63 light years away, and it's cosmically very young at 23 million years old. For context, 23 million years ago saw us in the Miocene period on Earth, in which whales and apes were already roaming the Earth. Beta Pic is surrounded by a dusty debris disk that is very bright in the near infrared, and that is what you are looking at here in this very Beta Picturesque image. Thank you. In 2009, a team in France, led by Dr. Anne-Marie Lagrange, used the direct imaging method to find an exoplanet in the Beta Pic system, which they called Beta Pic B. Very catchy name, we love it. But now Dr. Lagrange is back, and she is not messing around. Her team has analyzed over 10 years of data taken with the HARPS instrument at the La Silla Observatory in Chile. That stands for the High Accuracy Radial Velocity Planet Searcher, which, surprise, surprise, uses the radial velocity method to detect exoplanets. That method uses the slight Doppler shift of a star's spectrum that occurs when a planet is orbiting the star, since a planet's gravity will ever so slightly move the star itself. This method is very precise, but astronomers have to be very careful to account for any intrinsic variability in the star itself, or there can be multiple objects orbiting the star. This was published in the Nature, what are they called?
Journal.
Magazine? Journal. Nature Journal. On Monday. And the European team announced the discovery of Beta Pic C, a giant planet 9 times the mass of Jupiter, and it's orbiting on a 1,200-day year. The planet is 2.7 times the distance between the Sun and the Earth, but on a much more eccentric orbit than ours. Scientists say that more RV data will be necessary to investigate the properties of this planet, and future observatories, like the Extremely Large Telescope, not to be confused with the Overwhelmingly Large Telescope, or the So Big Telescope you can't even fathom it telescope. One day they'll build that, and then we'll get more information.
Cool. So, a star was observed to be escaping the Milky Way at 1,700 kilometers per second, which is really, really, really fast for astronomers. And for those who drive, which I do not, that's 3.8 million miles per hour. So that's very fast. And to give you an idea, the average star in the Milky Way travels at about 230 kilometers per second. So an average star with an average speed is usually bound to the galaxy and isn't flung away because, you know, gravity is a thing. However, if a star can travel fast enough, then it can overcome this force and actually escape the galaxy. And so one such star, this hypervelocity star S5HV-S1, was serendipitously discovered in the Southern Stellar Stream Spectroscopic Survey, which is S5 for short. So try saying that a lot of times. Which it's not exactly meant to look for these kinds of extreme stars. So this survey is meant to look for, you know, stars and stellar streams. But, you know, beggars can be choosers. So a team of researchers led by Sergei Kopasov tested multiple scenarios for how a star can have this high of a velocity. And they concluded that no massive star interaction, no supernova explosion would kick such a star to high enough velocity that we observe. And instead, the most probable culprit is interactions with our very own supermassive black hole, Sagittarius A. So by using the star's current trajectory, the researchers were able to trace back the star's origin to the galactic center. And when the star's So the most probable scenario is that the star was in a binary system. And when a binary system gets really close to a supermassive black hole, one star can get captured by the black hole, while the other star can get slingshot away with enough speed to be yeeted out of the galaxy. Yeet! Yeet! So that's pretty important. And finding more hypervelocity stars like S5, HVS1 is extremely exciting because then it would give us a better idea of how frequent close encounters of stars in a galaxy happen with our supermassive black holes. So that's pretty neat.
We have some news from the gravitational wave world. So gravitational waves are the now famous ripples in space-time that are created when massive objects collide or accelerate. We need highly sensitive detectors to find these very small warps in space-time. And even then, you need very highly energetic events to even be able to detect any signal at all. So the signal from a gravitational wave detector is analyzed to determine the masses of the object in motion. So that way you can deduce the type of astronomical event that has been detected. So if both objects are larger than, say, 5 solar masses, then you have probably found 2 black holes. If you find an object between 1 and 3 solar masses, it's more likely to be a neutron star. So if you've kept up with astronomy in the last few years, you know that in 2015, LIGO, the Laser Interferometer Gravitational Wave Observatory, announced its famous detection of 2 black holes colliding. And then a few years later, there was the announcement that a neutron star merger had been detected. So there's a third kind of gravitational wave that may exist, which comes from 2 kangaroos running into each other very fast. Nope, that's not right. OzGrav, the team in Australia dedicated to the study of gravitational waves, announced last week a detection from LIGO plus a signal from Virgo, which is the gravitational wave detector in Italy. So this signal is thought to come from 900 million light years away. And what's so interesting is the large difference in masses in the objects that are colliding. So one is more than 5 solar masses, and the other is less than 3. So according to OzGrav, the GW event was possibly caused by a massive black hole gobbling up a neutron star, or in more technical terms, a neutron star black hole merger, but that's boring. Professor Susan Scott of the Australian National University has the best description of the event, which is black hole Pac-Man instantly snuffs out the neutron star. So what you're looking at here is an artist's rendition, and that artist is named Carl Knox. But artist number 2 is named Jackie, and that's me, and I added a Pac-Man to help you understand this astronomical event. So I am your humble artist, What a Merger Jr., or should I call myself What a Neutron Star Merger Jr.? Ooh. I have no visual image for you, sadly. The Australian National University Sky Mapper telescope searched the sky for an optical counterpart to this signal, but there's been no light signature found for this merger. But this further suggests that the black hole might have gotten extra hungry and gobbled up the star hole, so we would never see anything. Ooh, spooky.
Ooh, spooky. All right. The Japanese space mission Hayabusa 2, which arrived in the near-Earth asteroid Ryugu last year, successfully collected its second round of asteroid debris, rubble, whatever, sample, whatchamacallit, after it sent an explosive to expose the asteroid's subsurface layers. So this set of samples would reflect more the original composition of the asteroid, which is believed to be one of the oldest objects in the solar system. Ryugu, yeah! Ryugu is a carbonaceous type C asteroid, which is a fancy term for a space rock made up of mainly dark clay and silicate rocks left over from planet formation. And so aside from having the Hayabusa 2 rover, there is also an orbiter that images the asteroid regularly via remote sensing. And a research team led by Seiichiro Watanabe analyzed the first year of the orbiter data from Hayabusa 2 and found that Ryugu is a spinning, top-shaped rubble pile. And that is verbatim the title of the paper that they published in the journal Science. But rubble piles is actually quite a scientific term. So they find Ryugu to have a density closer to that of water, which is, way lower than expected for an asteroid with its composition, which points to a picture where it has a lot of empty spaces in it, so it's quite porous. And the remote sensing images also show that a lot of the boulders on its surface exist. Lots of boulders, that Shrek thing. I like boulders.
That is a nice boulder.
That is a nice.
I like that boulder.
I want that boulder. So there's a lot of boulders here, so Donkey should go to Ryugu. Anyway, so these observations point to a scenario where Ryugu was formed from the accumulation of loose rocks bound together by gravity, ergo rubble pile. And so asteroids like Ryugu are believed to have introduced water and organic materials to Earth. So learning about these, rubble piles help us understand about how our own planet has formed. So we should stay tuned for more cool stuff once the samples get back to Earth. Cool.
Okay, we have one more story before astronomy not in the news, but we're going back to black holes for a second, but this time to a wavelength near and dear to my heart using the ALMA telescope. So I'm sending ALMA love to these researchers. Thank you.
Wow. Is that the...
So there are several methods for measuring the mass of the central black hole that exists in most galaxies. In optical or near-infrared light, the orbital motion of stars is a telltale indicator of the size of the object that these things are orbiting around, which is how the supermassive black hole at the center of our own galaxy was measured. And in some spiral galaxies, water masers will turn on, which can also be seen within these gas clouds that are orbiting the black holes, but those events are very rare, and so we're trying to come up with more new ways to weigh black holes, because that's something you need to do every day in your life. So a paper led by Dr. Benjamin Boisel, who is a postdoc researcher at Texas A&M, we'll forgive him for being an Aggie, it's still Texas, so. They investigate a new method for measuring the black hole mass in nearby elliptical galaxies using carbon monoxide kinematics. So about 10% of elliptical galaxies contain disks of cold rotating gas. The most abundant molecule in the interstellar gas is molecular hydrogen, but this is typically too faint to observe, so we go to the next most abundant molecule, which is carbon monoxide. This emits at millimeter wavelengths, so you can see this with very sensitive interferometers like ALMA, the Atacama Large Millimeter Array, which is in the Chilean desert. So the next thing you need to make this measurement is very high spatial resolution, because you basically want to measure a velocity differential. So you would measure the Doppler shift in the velocity in different parts of the disk, which you're seeing in this lovely rainbow, and this is known as rotational kinematics. So the team chose NGC 3258, which is a giant elliptical galaxy about 100 million light years away from here, and they were able to resolve the gas only 65 light years away from the black hole itself, where the gas travels at 3 million kilometers an hour. So I got you beat. Whoa. Anyways, they have to use a model to interpret the disk's rotation, including the presence of additional stars that might be near the black hole, the inclination and the warping of the disk, and a few other parameters. Basically, at the end of the day, they measure a black hole that is 2.25 billion solar masses, with a precision close to 1%. So talk about all amazing. That's all I got, folks. One more.
Anyway, astronomy not in the news. So 22 years and a day ago, the first Filipino-owned satellite launched into space. And this is particularly interesting to me because I'm Filipino and I was not aware of this till yesterday when Jackie pointed it out to me. So I was actually not the one who found it out, it was Jackie. So thank you, Jackie.
You're welcome.
Anyway, so the satellite was originally named Aguila 2 after in honor of the Philippine national eagle, the Philippine monkey-eating eagle, which is pictured over here with all of its glory. Hello. And that's our national bird. Anyway, so the satellite isn't the kind that faces up to the sky in order to observe the universe. This is the other kind that faces down to the Earth and provides telecommunication services and broadcasts to the Asia-Pacific regions and even reaches Hawaii. So it was launched on August 19th, 1997, so I was barely 3 years old, by Mabuhay Philippine Satellite Corporation using a Chinese Long March 3B rocket in Sichuan Province, China. And in 2009, it was renamed to ABS-5 after being bought by Asia Broadcast Satellite, ergo ABS. And in 2011, it was renamed to ABS-3 after being repositioned 3 degrees west. But it was still owned by Asia Broadcast Satellite, so it's still ABS. And 22 years later, my country has launched 3 other satellites, microsatellites named Diwata 1 and Diwata 2, and Diwata means nymph or fairy, and nanosatellite named Maya 1, which means sparrow. So we have a bajillion more words for flying creatures, so we definitely have, a lot more of satellites to name, but just, give us the money. So that's it for the news.
Thank you.